The DiJet search is an analysis performed in the ATLAS experiment, where we analyze proton collisions produced by the Large Hadron Collider, where at least two high-energy jets of particles are produced. A jet is a spray of particles that all go in roughly the same direction. Jets are the most common objects we observe in ATLAS and generally in hadron colliders. And the reason is that when we collide protons, the dominant processes are those of quantum chromodynamics, whereby hadronic jets are mostly produced.
An excess of events might point at new heavy particles produced in the interaction which decay to two jets. One common hypothesis for these objects is excited states of quarks, which would hint at a substructure and underlying physics at a smaller distance scale. At this short distance scale, this might also be visible directly in angular distributions where a deviation from the QCD scattering might be visible. In addition to a potential excited states of quarks or contact interaction between them, one hypothesis could be strong gravity, where we might observe production of gravitons.
The first thing we do is look for a local excess of data which are all produced around the same mass. That would be an indication that a new particle of that mass is being produced. The first thing is to suppress the background by introducing a cut which requires both jets to be relatively central. After the background is suppressed, we scan the mass spectrum for a local excess, having minimal bias about where the excess may be or how wide it could appear.
For the next piece of the analysis, we look in detail at the angular information. So we make a loose cut on the DiJet mass. We look at events with at least 2 TeV of DiJet mass. This gives us a large enough sample that we can bin the data in fine bins of an angular variable called chi. So that the chi variable, for low chi, we have events where both jets are relatively central, where for high chi, we have events, for example, with one jet forward and one jet in the backward region of the detector. So QCD predicts a relatively flat chi distribution, and most models of new physics give an excess of events at low chi. So we compare the chi distribution observed in data with a prediction from simulated events from standard model jet production QCD.
Instead of finally resolving the shape of the angular distributions, we can in addition also simply look at the fraction of central events. This allows to measure the evolution of these angular distributions with mass. The resulting observable is sensitive to both resonant and non-resonant models of new physics and is thus a hybrid of the two observables presented before.
In summary, we have analyzed the full data set from the first full year of LHC operations. We've looked at DiJet events with two highly energetic jets, and analyzed the DiJet mass and angular distributions to look in a model-independent way for new physics. So far, we have no evidence for new physics. So instead, we look to particular models of new physics, and we set limits. So we set the world's best limits on excited quark production and on quark substructure, for example. We also consider simplified DiJet mass distributions in an effort to make it easier for theorists to apply our constraints to their models. This activity will continue. In 2011, we've already taken much additional data. This year, the data set may be 50 times as large as what we present in this paper. So please stay tuned. A discovery may be just around the corner.